For 60 years, spaceflight ran on violence, controlled explosions hurling metal into the void. Now, thousands of satellites move on a whisper, thrust too faint to lift paper. That whisper pushed one NASA spacecraft to orbit two worlds no chemical rocket could ever reach. Today, it steers Starlink, drives Psyche toward a metal asteroid, and ends the chemical thruster's reign. The engine is called ion propulsion, and it never touches fire. This is the quiet engine rewriting how humanity moves through space. Hit subscribe because the way we move through space just went silent. Every satellite that reaches orbit carries a hidden countdown clock, and it has nothing to do with electronics failing. That clock is fuel. For 60 years, spacecraft have leaned on chemical thrusters to survive in orbit. Small hydrazine engines fire in short, violent little bursts to nudge a satellite back into position. It is nearly the same basic design NASA flew on the Apollo missions more than 50 years ago. Mix propellant, ignite it in a tiny chamber, and blast hot gas out through a nozzle. Fast, powerful, simple. But every single burn wastes propellant mass that can never be replaced once a satellite reaches orbit. Today, that limitation has become a real crisis. Companies are no longer launching a handful of satellites. Satellite constellations are the new normal now. Starlink alone operates more than 7,000 spacecraft in orbit. Tens of thousands more are planned across multiple companies, each satellite needing constant tiny adjustments to survive. Every correction keeps a satellite in its lane, avoids collisions, and steers it safely out of orbit at the end. If every one of those satellites relied purely on chemical thrusters, the fuel would run out fast. A dead satellite does not just disappear. It becomes uncontrolled debris, drifting through orbits other spacecraft depend on. Engineers needed something radically more efficient, something that could sip propellant instead of gulping it down. The answer came from a completely different kind of engine, one that replaces combustion with electricity itself. Instead of one violent kick, it delivers a continuous, gentle push that can last for years at a time. That engine is called electric propulsion, and it is quietly becoming the default choice for an entire generation of spacecraft. Ion propulsion sounds like something from science fiction, but the physics behind it is remarkably simple. Inside the engine sits a tank of xenon, a heavy, stable gas that ionizes easily under electricity. An electric current strips electrons from xenon atoms, turning neutral gas into charged plasma. A magnetic field traps those electrons in a spinning ring, keeping the ionization process running continuously. An electric field then accelerates the positively charged xenon ions, hurling them out of the thruster at incredible speed. Those ions can leave the engine at speeds 10 times faster than gas from a chemical rocket. That speed is what makes the engine so efficient, even though the actual thrust feels incredibly weak. A single Hall thruster produces roughly the same push as the weight of one credit card. But unlike a chemical engine, it can fire almost continuously for months or even years without stopping. Over that time, tiny amounts of thrust add up to far more total speed than any chemical burn. Engineers measure this efficiency using something called specific impulse, and electric engines dominate the comparison completely. A chemical thruster might reach a specific impulse of around 300 seconds. Hall thrusters exceed 1,600. That difference means dramatically less propellant mass for the exact same mission launched into orbit. This April, Rocket Lab began mass-producing these engines, building over 200 a year to meet demand. In 2023, NASA launched a spacecraft called Psyche, aimed at a strange, metal-rich asteroid deep in the solar system. This asteroid, named 16 Psyche, may be the exposed core of an early planet that never fully formed. NASA's first real test of electric propulsion came decades earlier, in 1998, with a probe called Deep Space One. Reaching it required an engine that had never flown this far from Earth before, the Hall effect thruster. 4 Hall thrusters, powered by 2 enormous solar arrays, would carry Psyche across nearly 3 billion miles. Psyche's own launch was delayed a full year after a software testing issue grounded the mission in 2022. Engineers like Julie Lee spent years preparing a system that had to work perfectly, with no way to repair it in deep space. That confidence came from Dawn, the first spacecraft ever to orbit 2 separate worlds using ion power alone. In April 2025, something went wrong. Pressure inside the xenon fuel line began dropping unexpectedly. The thrusters that were supposed to fire almost continuously for years suddenly went silent. For weeks, the team worked to diagnose a problem happening 200 million miles away. They found the answer, switched to a backup fuel line, and by June, Psyche's engines were firing again. No astronaut could have fixed it. The entire recovery happened through code, patience, and remote engineering alone. It is a reminder that ion propulsion is not just physics. It is also trust in a machine nobody can touch again. Psyche is expected to reach its asteroid target in 2029, 6 years after leaving Earth on a whisper of thrust. Today, Psyche is still accelerating, its engines whispering across the solar system toward a world made of metal. Psyche is not alone. This same quiet technology now guides missions from Mercury to the asteroid belt and beyond. The numbers behind this shift are staggering, and they explain why virtually every satellite maker is embracing it. Electric propulsion can cut propellant requirements by as much as 90% for the exact same maneuvers. A typical geosatellite might once have carried more than 2,000 kilograms of chemical propellant. Switch to xenon and Hall thrusters, and that number drops to only a few hundred kilograms. That freed up mass becomes extra payload, more instruments, more capacity, all without a heavier rocket. Across an entire satellite, mass savings average between 30 and 50% compared to chemical designs. By 2024, more than 60% of new commercial satellites launched already carried electric propulsion on board. Communications giants like SES, Intelsat, and Eutelsat have committed to transitioning their fleets to all-electric platforms. Even geostationary satellite orders have shifted, with electric designs now making up nearly half of all new contracts. Those savings translate directly into dollars. The European Space Agency estimates $2 to $4 million saved per mission. Low-orbit missions are catching up fast, too, with electric propulsion use climbing 35% year over year. Satellites already in orbit are getting extended lifespans as an in-orbit servicing using electric propulsion grows by 25%. But the technology is not without trade-offs, and honest engineering means admitting them. A chemical satellite can reach geostationary orbit in about 1 week after launch. Going all-electric takes far longer, spiraling outwards slowly for 3 to 6 months. For some operators, that wait is worth it. For time-critical missions, it still is not. This is why many satellites now fly hybrid systems: chemical thrusters for the fast climb, electric for everything after. It is not a total replacement, it's a careful redistribution of the job each engine does best. And as more constellations launch, that redistribution keeps tilting further toward the quiet engine. Every technology that reshapes an industry forces a harder question. What does this progress actually cost? Ion propulsion runs on xenon, a gas so rare it makes up barely a trace of Earth's atmosphere. It has to be extracted as a byproduct of industrial air separation, an expensive and painfully slow process. For years, a large share of the world's xenon supply came from just 2 countries, Russia and Ukraine. When that supply chain fractured, xenon prices did not just rise, they spiked to genuinely staggering levels. At the worst point, prices reportedly reached tens of thousands of dollars per kilogram, an almost unusable cost for many missions. An engine praised for efficiency suddenly depended on one of the most fragile supply chains in industry. SpaceX responded by switching newer Starlink satellites from xenon to argon, a far more abundant, cheaper gas. but argon is less efficient as a propellant, a genuine trade-off between cost, supply, and raw performance. Other companies are testing alternatives entirely, including iodine, which is solid at room temperature and easier to store. None of these alternatives are perfect yet. Each one trades away something the last one solved for. This is the quieter side of the story, the one that rarely makes it into a triumphant headline. There is also a bigger structural question hiding underneath all of this. Why are we launching so much? Cheaper, more efficient propulsion does not just improve existing missions, it makes launching thousands more satellites easier. More satellites means more orbital traffic, more potential for collisions, and more pressure on an already crowded sky. Ironically, the same quiet engine also helps here, letting dead satellites steer themselves down safely at mission's end. So the technology both fuels the crowding problem and offers one of the few tools to manage it. That contradiction is not a flaw in the reporting, it is simply the honest shape of the technology. There's a third layer too, one that reaches beyond commercial satellites and into national strategy itself. Countries that control xenon supply or master alternative propellants first gain quiet leverage over an entire industry. Propulsion, once a purely technical detail, has quietly become a geopolitical asset worth competing over. None of this erases what ion propulsion has achieved. It simply means the achievement comes with real complexity attached. The engine that replaced violence with a whisper still has to answer for the cost of that whisper. The loudest era of spaceflight is ending. The next one will hardly make a sound. Chemical rockets will always be needed to leave Earth. That has not changed and will not change. But once a spacecraft reaches orbit, the future belongs to something almost silent, a whisper of xenon, patient enough to cross billions of miles without ever running dry. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it every single week. We'll see you in the next one.